Okay, in this lesson I want to introduce two new quantities, work and power. So first just to define what work is, and then we look at a kind of a little equation. We'll draw up one of our little multiplication triangles, change the subject of the formula. We'll do something similar for power, and we'll look at one or two little examples. Work is a measure of energy transfer that occurs when an object is moved over a distance by an external force. So when an object is moved over a distance, in order for work to occur, an object has to travel over some distance. If it does not travel over some distance, no work has occurred. Also, there has to be some force on the object, so work depends on those two things, the distance traveled and the external force. If the force is constant, which it always will be on our course, if the force is constant, work may be computed by multiplying the length of the path traveled by the component of the force acting along the path. So work is generally defined as follows. So it can be computed by multiplying the length of the path followed, or the displacement, by the component of the force acting along that path. So it's force multiplied by displacement, or force multiplied by the change in position, if you like. And note the force along that direction. So you'll often see it written like this, F sub x times delta x. So it's the force in the direction of the displacement multiplied by the displacement. Okay, so if we have some object here, and maybe there's a string pulling on it, and there's some tension force here, and maybe that tension force causes this object to travel from point A to point B, and suppose those things are, let's just say 10 units apart. Well, then the work done on this would be 10 meters multiplied by t, force by distance, t by 10. Okay, notice the units here as well. We're talking about displacement, the units will be meters. We're talking about a force, the units would be newtons. Newton meters are the units of work. We tend to call those joules, unit of energy. Now it's also a measure of energy transfer. So work has the same units as energy, joules. Okay, so remember work is measured in joules. Suppose we have this situation where we have some box being pulled along here by a person, and you can see that the tension in the rope here is acting not quite horizontally. The tension in the rope is acting up along this direction. So there's my tension in my rope, and you can see if enough force is applied, this box will slide horizontally across the floor. It's not going to fly up to the person's shoulder as the person walks along from left to right. So if we think about this tension, and we can resolve that into its horizontal and vertical components, and remember, if this is theta, let's just call it theta. Well, the horizontal component here will be t cosine theta. The vertical component will be t sine theta. So that vertical component might help reduce friction or something, but this is really the force that's pulling it, t cosine theta. So in this case, the force, remember, work is force by displacement in the same direction, though. We're talking about F sub x times S sub x. The force and the displacement have to be in the same direction. So in this case, the force would be t cosine theta multiplied by the displacement, whatever that is. So let me write that as S displacement by t cosine theta. Okay, so that's work. S by t cosine theta. And the units are joules. We generally just give a capital J. S by t cosine theta. Work is considered to be a scalar quantity. It's actually the dot product of two vector quantities, so it is considered a scalar quantity. So work, force by distance, essentially. Remember that. And if the direction of tension here is different to direction of motion, well then you will have to resolve your tension force in some way. Power is the time rate of doing work or delivering energy. So power is simply defined as work done divided by the change in time. Okay. My units for power there would be joules per second, and those units are generally called watts. So power is equal to work done divided by the change in time. Okay, so in order to calculate power, I need to know how much work has been done and how much time it has taken to do that work. Increase in work and increase in power. An increase in time would mean a decrease in power. If it takes longer to do the same amount of work, well then there's less power involved. So work, define work. Work equals force by displacement along the same direction. Remember, get used to changing the subject of the formula. Force by displacement giving me work done, assuming the work is the force is constant, of course, which it always is in our course. So if I know the work and the displacement, I can calculate the force. If I know the work and the force, I can calculate the displacement as well. So getting used to changing the subject of the formula. If the force and displacement are in the same direction, work is positive. If they're in opposite directions, work is going to be negative. Power is defined as work done divided by time taken. So again, just like before, work done divided by time taken, that's giving me power. So if I know the power and the time, well, I can calculate the work. And if I know the work and the power, I can calculate the time taken. Okay, so you need to know the definitions for these things. You absolutely need to know these equations by heart. And just get used to them. Practice. So calculate the work done and power output in moving this object 300 meters in 5 seconds. Notice there's maybe a tension force here pulling this along to the right at 80 newtons. Work is force by displacement. The force here is 80. The displacement, well, it's been moved 300 meters. Okay, make sure your units are in meters, by the way, and your units for force are in newtons, because 1 newton meter is 1 joule. So 80 times 300, well, 8 3s is 24. And then we've 3 zeros there. So it's 24,000. And my units are joules. Power is defined as the work done divided by the time taken. So we're going to say the power is going to be 24,000 divided by 5. Notice my units here are joules. My units here are seconds. 5 into 24, or 40. That's 4,800. And my units here would be watts. 4,800 watts. Okay. Calculate T and the power output in moving this object 30 meters in 5 seconds. So I'm trying to find the force here applied. I'm told the object is moving 30 meters in 5 seconds. I'm also given down here that the work is 300 joules. So remember how we define work. Work is defined as force by displacement. So I want to find the force here, T. So force is going to be equal to work divided by the displacement. The work here is 300 joules divided by the displacement, which is 30 meters. So my force is going to be 300 divided by 30, which is 10 newtons. My power, well, my power is work done divided by time taken. Average power, work done divided by time taken. That's the definition. My work done here is 300. It's given. Time taken is 5. Make sure your units are, work should be measured in joules. Time should be measured in seconds. 300 divided by 5. That's 60 watts. That's the power. So the work done, or the force applied, is 10 newtons. And the power output is 60 watts. Calculate the work done on T and moving this object 30 meters in 2 seconds. So I'm trying to find the work done. To find the work done, I need to know the force. Work is force by displacement. I don't know the force, so I can't go that route. However, I am given the power. I am given the power output here. And power is defined as being the work done divided by time taken. Okay, so power is the work done divided by time taken. So the work can be defined as the power multiplied by the time taken. In this case, the power is 150 watts. The time taken is 2 seconds. So the work done is 300 joules. So work done here, 300 joules. How do we define work? Well, work is force by displacement. I want to find the force applied here. So force is work divided by displacement. The work here is 300 joules divided by the displacement 30 meters. So the force being applied here is 10 newtons once again. Okay. Note, in these two examples, we applied a force of 10 newtons in moving an object 30 meters, so the work was 300. We applied a force of 10 newtons in moving an object 30 meters, so the work is 300. However, the time here is different. This was 2 seconds. In the previous example, it took a bit longer. That would mean if it's taking longer to do the same work, that means it's less powerful. So that force is less than this other force here. Okay. A moving car skids 20 meters before coming to rest. Calculate the work done. How much work was done on the car by friction. Okay. And so a moving car. Well, let's just calculate the work done. Actually, I'm going to just ignore that second part. So a moving car skids 20 meters, coming to rest. Calculate the work done. So suppose the car is moving to the right. Let's call it a right positive system. And it skids. In other words, somebody has applied the brakes to the car, which means that friction is a force acting here, and it's acting to the left. So there's my force in this case. Note, if this is a right positive system, that force will be negative. The car skids 20 meters, so it travels from there to there, a distance of 20 meters. Work is defined as being force multiplied by displacement. The force here is going to be a negative force. So work is going to be that force multiplied by 20. So work is going to be equal to 20 by whatever that friction force is. Okay, well, how do we calculate friction? Well, friction, the maximum value for friction is mu times the normal reaction. Here the value for mu, the coefficient of friction, is 0.8, and hopefully you can see from the diagram the weight of this object is 1000 g, so the normal reaction is going to be 1000 g. The car doesn't sink into the ground or fly up in the air, so It's going to be 0.8 times 1000 G, okay, which is going to be 800 G. Okay, so if I let G, let's just leave it in terms of G like that. So that's my friction force. Notice that's acting in the negative direction, so my work is going to be equal to the positive 20, displacement positive here, multiplied by the 800 G, which is going to be negative 800 because it's a negative force. 20 times negative 100, that's negative 2816, and then 3 zeros. G. So the work here is negative 1600 G joules. That's the work. It's work, it's just force and displacement in opposite directions, so the work is negative in this case. Okay. I'm going to skip past that one. And let's have a look at this final one. I lift a 1 kilogram weight, half a meter, with constant velocity. What is the work done by gravity on the weight? Okay. I lift a 1 kilogram weight, half a meter, with constant velocity. Let's just look at that. There's a 1 kilogram weight. The weight down would be 1g. And if it's moving with constant velocity, that means there's no vertical acceleration, which means the upward force must also be 1g. What is the work done by gravity on the weight? The work done by gravity on the weight is going to be equal to, well, let's define this maybe as an up positive system. The force by gravity is down, so it's negative 1g, multiplied by the displacement. The displacement, I'm moving at half a meter, 0.5 or half, so we get negative g over 2, and my units here are joules. So gravity is doing negative g over 2 joules of work on the object. And what is the work done by me on the weight? I'm applying a force, it's moving some distance, while the work by me on the object, I'm applying a force, it is moving some distance, so there is being work done. That work is going to be the force that I'm applying, which is 1g, multiplied by the displacement, which is half a meter. So again, it's g over 2 joules of work. So I'm doing g over 2 joules of work on the object. Gravity is doing negative g over 2 joules of work on the object, and that's how that's working. Okay, so work and power, learn off the definitions, practice a few questions. We're moving into chapter 6 now of our textbook, so keep practicing. In our next class I'll look at applying some angles in there and thinking about how they work.